Okay, good morning. Any questions from yesterday's class? And please note that whatever we just got in, these are all very important concepts. You need to understand them clearly. And some of them you must have already studied as a part of your mechanics of materials or structural analysis. And if you don't have any questions, let me actually start. So this is where we left yesterday. Okay. Just let's go through this proof stress. What is the meaning of this proof stress? The stress that will cause a specified small permanent extension of a tensile test piece. Commonly, the stress produced to commonly the stress to produce 0.2% extension. That you make a note of it. Stress to produce 0.2% extension is quoted or expressed in Newton per mm square per steel. That is what is proof stress. This value approximates to the yield stress in materials not exhibiting a definite yield point. So depending on the type of steel, some of the steels like mild steel will exhibit a definite yield point, and whereas this high strength steels, you will not be able to observe, or they are not going to exhibit any definite yield point. In such cases, we need to get this yield stress value, we need to use this one. That is the stress which corresponds to 0.2% extension, that is taken as yield stress. So let's quickly see. Yesterday, I have not shown you yesterday stress strain curve for mild steel. Okay, I have not shown you this one. This is how it looks like, stress strain curve for mild steel, and you must have seen this as a part of your mechanics materials course. Okay, and you can see here various salient points on this curve are indicated. Proportionality limit, this point A corresponds to proportionality limit, point B is the point which corresponds to the yield stress. After that, you have some yield plateau. Okay. Again, after point C, the stress strain curve rises up, and there are two. One is dotted curve is shown, another one is solid line. So this dotted one is like true stress, corresponding to true stress. What is true stress and other things? You need to go back to your mechanics of materials and revise all those concepts. Okay, and this portion after C, stress strain curve or the stress value is raising, and this is what is called strain hardening portion. Okay, this is strain hardening portion, and this portion between B and C is perfect plasticity or yield. This is also called yield plateau, and the initial portion from 0 to A, that is linear region. Okay, stress is going to be proportional to strain, and the slope of this is going to match with your Young's modulus or modulus of elasticity for concrete, for steel, modulus of elasticity for steel. Okay, and anyway, this peak point is the ultimate stress. And in this region, necking is going to happen. If you take a tensile test specimen and do the testing, and that is like in this region, or when the stress is in this region, you will be observing necking and reduction in the cross sectional area, such kind of things. Because of that only, when necking is going to happen, cross section of the specimen is going to reduce. That's why the curve is getting splitted up. Which cross sectional area you are using to calculate the stress, that is where the difference, engineering stress and true stress. Okay, anyway, this is the stress strain curve for mild steel, and this is actual, you can say this is actual stress strain curve. But what code is saying is, you forget about all this like the strain hardening portion and other things. And code is giving for mild steel, code is specifying to use, or mild steel is a steel which exhibit definite yield point. So code is saying use this curve. This is like idealized curve, idealized stress strain curve for mild steel, and stress is going to be varying linearly with strain up to the yield point. After that, it's going to the curve is going to get flattened, and the stress value remains constant at the Fy value. Okay, and once you have this, design stress strain curve is obtained by reducing this peak point with this one. Anyway, let's see this. Sorry, let me show you whatever curve that is given in IS 456. Okay, here, whatever curve that is given in IS 456, Fy, and then a design curve is obtained by Fy divided by 1.15. Fy divided by 1.15. And once again, I suggest, because we are getting into the design aspect, so you should, all of you should have pen and paper with you and also calculator with you. Can somebody quickly tell me what is 1 divided by 1.15? 1 divided by 1.15.
0.67.
Huh? 1 divided by 1.15.
0.67.
0.67. No, 1 divided by 1.15.
0.869.
0.87.
Then why people are saying like that? That is what this one is. That is what this curve is showing. Instead of showing it as Fy divided by 1.15, directly that 0.87 Fy is shown here. Okay. Anyway, this is the stress strain curve for mild steel. What about high tension steel? That is actually given in IS 456. You need to also have code book with you. Okay, page 70. Figure 23 is giving representative stress strain curve for reinforcement, both for yields exhibiting definite yield point. The bottom one is for yields for steels exhibiting definite yield point. The top one is for cold work deformed bar or high yield strength, HYSD, high yield strength deformed bars. For those, this is the stress strain curve. Okay, and now what are these dashed lines that are indicated? What are these dashed lines that are indicated? And you just recall the definition of proof stress. Proof stress is 0.2% extension. Stress corresponding to 0.2% extension. So this is the initial line, or the linear portion of the stress strain curve, and parallel to that, if you draw a line starting at 0.2% strain value, that is 0.202, you draw a line. This dotted line is parallel to the solid line, initial solid line, and it is starting at strain equal to 0.202, and where that is going to intersect, the given stress strain curve, that is corresponding to your yield stress value. We can see here. Let me magnify, then it may be better for like. So you can see here, this line is going, this line is parallel to the initial stress strain curve, and only thing is it's starting at a strain value of 0.2%. That is what the definition of yield stress, and it is drawn, this dotted line is drawn, and where it is going to intersect the stress strain curve, that corresponds to your yield point Fy. Is it clear? And similarly for other strain values, this point is this point 201 is corresponding to 0.1% extension, and similarly other things, 0.07% extension, 0.03% extension, 0.01% extension. And what is the exact value? What is the exact value of these? These are all tabulated. These are also tabulated in your IS. Let me show you that. This is nothing but SP16. SP16 is giving you all those details. Okay. So the values which are shown on the figure, they are actually noted here. Stress corresponding to 0.8 Fy nil. Corresponding to stress of 0.8 Fy strain, inelastic strain. Inelastic strain is nothing but permanent extension or extension of that. The definition is like, no, if you see proof stress, it is 0.2% extension. So that's why it is written inelastic strain. So corresponding to 0.8 Fy. So let's see that 0.8 Fy in the figure. Corresponding to 0.8 Fy, it is lying on the initial linear portion of the stress strain curve. So there is not going to be any permanent or inelastic strain. So corresponding to 0.8 Fy, inelastic strain is 0. Corresponding to 0.85 Fy, inelastic strain is 0.301. Corresponding to stress is equal to 0.9 Fy, strain is 0.303. Subsequently, all the other things. Those values are all actually given here. Is it clear? So using this information, you can reproduce this curve. You can reproduce this curve, stress strain curve. And if you want design stress strain curve, you just divide this Fy with 1.15 or multiply with 0.87. Whatever you just try to calculate, that 0.87, that one. Okay. So then you are going to get design curve. Design curve for HYSD bars or high strength steel like Fe415 or Fe500. This is going to be your design stress strain curve. Okay. Any questions here? And now before we proceed further, I want to also show you here. This curve is also given in your SP16. This curves for Fe. I don't know whether you are able to see here properly or not. Let me magnify only a portion of it, then you will see better. So you can see here. This curve is for Fe500. Okay, and the design curve, corresponding design curve is obtained by dividing 500 with 1.15, and you are going to get this curve, design curve for Fe500. Similarly, Fe415 steel and design curve for Fe415 steel. And other salient points, just know whatever we discussed, 0.2% strain, 0.1% strain, all those things are those corresponding dotted lines, or whatever the dotted lines we have seen in the previous figure, those are all again reproduced here. Okay, and now for Fe500 steel and Fe415 steel, corresponding to these strain values, what is going to be the stress value? So those are all given in your for design curve. For design curve, corresponding stress value and corresponding strain value, they are given in SP16, Special Publication 16. And I just want to tell you that this SP16 somehow the size of this file is big. And recently when I try to upload on the Moodle, it's not getting uploaded. But you can go to Moodle website and click on last year's that is July November 2019 CE3060. There on the Moodle SP16 is there. Okay, so you look at it, and if you have any difficulty, you let me know, because via email also it's difficult. I think I need to put somewhere in the Z drive and then have to share the link. But you try that one on the Moodle last year course the website, it is there. Okay, so now coming to this one, stress strain curve for FE415, FE500. The salient points we already noted, 0.8 Fy, and here instead of Fy, Fyd is written. Why? What is this Fyd? Fyd is nothing but Fy divided by 1.15. Fy divided by 1.15. So if you want to reproduce the design stress strain curve for FE415 or FE500, you make use of these values. Okay, so FE415 yield Fy value is 415. So 415 Newton per mm square divided by 1.15 is going to be 80% of that. 0.8 times Fe, this 415 divided by 1.15 is going to give you this. Quickly, can somebody cross check that? This value, whatever this, sorry, this value, stress value, 288.7, what I am saying is it is equal to 0.8 multiplied by 415 divided by 1.15. Please check it. You should be quick, understand. What is that? Is that matching?
Yes, sir.
And you can cross check this one. You take Fy is equal to 500. 0.8 multiplied by 500 divided by 1.15. Is it matching?
Yes, sir.
Okay, please, all of you, you need to pay attention, understand. It's not like Ramayana, Mahabharata or something. It's not, I'm not telling story, understand. You need to pay attention here and understand everything. So the idea of this table, which is given in SP16, is if you want to reproduce this entire stress strain curve, design stress strain curve, you can make use of these salient points. Okay, that's why the title is salient points on the design stress strain curve for cold worked bars. Okay, this is given in SP16, and rest of the values you can cross check. And please note that only some few points are given. In between, if you want, you can use linear interpolation and get the intermediate values. Okay. Any questions? Professor Amlan, you want to add something?
See, one important point I wish to mention, that for the concrete stress strain curve, the material partial safety factor is used from the very beginning itself. If you look into the characteristic curve versus the design curve deviates from the characteristic curve right from the origin. Whereas for the steel, the material safety factor is not applied initially. Till 0.8 times Fy, there is no material safety factor. After that, from 0.8 Fy onwards, the design curve deviates from the characteristic curve. Hence, if you look into the modulus of the design curve is same as that of the characteristic curve, which is 200 gigapascal. Whereas for the concrete, it is not so. Okay.
Is it clear? Is that point clear what Professor Amlan is pointing out? Please note that these are the kind of questions we expect from you. So you can see here stress strain curve for concrete, which we discussed, and with whatever explanation Professor Amlan has given, you can just think about it, okay? And this is the stress strain curve for concrete, idealized curve and design stress strain curve. Everything is given in the same figure, and same thing here. For
let me just explain a bit further. The reason behind this is it has been observed that in concrete, if the strength reduces, the initial modulus also reduces. That means if it is a poor concrete in terms of strength, it is also poor in terms of stiffness. Whereas for steel, even if there is some variation in the yield value, the stiffness does not change. The stiffness remains more or less same. And hence, the partial safety factor is not applied in the initial part of the curve for the steel. Okay.
yeah, somebody has some question. No questions? So let's proceed further. And I want to quickly complete this storytelling, and then I want to get into the real stuff, at least before we close for today. Okay. So let me quickly go through this. This is some details about this reinforcement. Let's quickly go through this. Okay. As concrete is strong in compression but weak in tension, steel bars are used to reinforce concrete to resist tensile stresses resulting from the applied loads. Additional reinforcement is also occasionally provided to reinforce compression region of the concrete beam section. Also in columns, such reinforcement is necessary for heavy loads in order to reduce long-term deflection. Material to be used for reinforcing the concrete must possess the following properties: high yield strength, high modulus of elasticity, ability to develop bond with concrete, good bond with concrete, coefficient of expansion which is nearly equal to that of concrete, and easy availability. So what kind of material can be candidate for this kind of thing? Steel. Steel as reinforcement satisfies all the above requirements. The resulting composite material is ideal because as concrete sets, it contracts and thus grips the reinforcement. This addition between concrete and steel to work together as a single material. The addition between the concrete and steel. Okay. So let's quickly note down few points related to reinforcement, and then we'll go to the design philosophies. Okay. Anyway, we already looked at this. Type of steel commonly used for reinforcement are mild steel, high medium tensile steel, hot rolled deformed bars, cold twisted, high yield strength deformed bars. These are some of the types of steels that we'll be using, and hard drawn wire fabric, steel wire fabric. In all cases, the modulus of elasticity of steel shall be taken as, yesterday you already noted, 200 gigapascals. Typical stress strain curves are shown here, and also idealized curves. Okay.
Okay, let me just make a point here. In the yesterday's class, for concrete, we saw that the modulus was related to the strength. E was equal to 5000 root over FCK. That means if the strength changes, the modulus is also changing. But whereas here you see, for the steel, for any grade, modulus is same. It is written in all cases, the modulus of elasticity shall be taken as 200 gigapascal. This is an important aspect, that for steel, we do not change the modulus with strength.
Okay. Anyway, let's quickly go through some of these points. Steel reinforcing bars are generally round in cross section since they possess the maximum possible perimeter to provide a better bond with concrete. To minimize slippage of bars relative to surrounding concrete, lugs or protrusions or projections called deformations are rolled on the bar surface. The lugs generally have an average spacing not exceeding 0.7 times the nominal diameter of the bar and height of at least 0.04 to 0.05 of the times of the nominal diameter. Also, they must be present at least 75% of the nominal bar perimeter. Okay, and these are some of the specifications related to that. These protrusions. The deformations are placed so that the angle of the angle to the axis of bar is not less than 45 degrees. Generally, longitudinal ribs are also present on the surface of bar. Okay, and the nominal diameter of deformed bars is equivalent to that of plain bar having the same mass per unit length as deformed bar. This is what I explained to you yesterday, how to get the equivalent diameter of a deformed bar. The steel reinforcement is normally designated as Fe250, Fe415, Fe500. The corresponding yield strengths are 250, 415, 500 MPa respectively, and generally have well-defined yield points. For mild steel it is there, but for Fe415, 500 we need to go with 0.2% proof stress. The important tests conducted on reinforcing bars are tension test and cold bend test. The tension test is performed to determine stress strain curve, yield stress or 0.2% proof stress, and ultimate strength of reinforcing bars, whereas cold bend test is conducted to determine whether steel bars can bend without fracturing. Please note that when we are actually making use of the steel bars for reinforced concrete, the purpose we need to bend those bars. So when you are bending those bars, like at 90 degrees or 135 degrees or even 180 degrees bend, the bar should not develop cracks or anything on the surface or anywhere. Okay, so if you take a simple this one paper clip and try to bend it back and forth few times, you can observe some cracks. Such kind of things, this cold bend test is similar to such kind of test for rebars. Okay, the test specimen is bent until two sides of the specimens are parallel. The internal radius of bend must not be greater than the diameter of the bar for bar diameter up to 25 mm and 1.5 times the diameter of the bar for diameter greater than 25 mm. Anyway, these are some specifications related to that bend test. Okay, and these are the routine tests that we will be performing on any sample of reinforcement bars that come to the site. We'll make sure these tests, the steel that we are adopting for construction satisfies these specifications which are given in the code. Okay, just for information, I'm going through all this, and we'll quickly go through this. Mild steel bars, minimum specified yield strength of mild steel bars conforming to IS 432 is 250 MPa. Among all kinds of steels, it is the most ductile. Typical stress strain curve for mild steel bar used in reinforced concrete construction loaded monotonically in tension. We already looked at stress strain curve. Okay, the curve exhibits an initial linear elastic portion, yield plateau, strain hardening region range in which stress again increases with strain, and finally a range in which stress drops off until fracture occurs. The stress at the yield point or yield strength is very important property of steel reinforcement. Mild steel, when used as reinforcement, can yield on overloading, resulting in excessive cracking in concrete and thus giving sufficient warning before failure. Okay, mild steel can yield on overloading, resulting in excessive cracking in concrete, giving sufficient warning before failure. Because of the easy availability of high yield strength bars, use of mild steel is limited. However, due to its higher ductility, it can economically used for secondary reinforcement. And we'll see what is the secondary reinforcement. Usually, like a ties you can have for shear reinforcement or somewhere we can make use of these mild steel bars. Okay, so due to higher ductility, it can economically be used for secondary reinforcement and in blast and earthquake resistant structure. The main important feature is its ductility is more. Okay, mild steel bars can be plain or deformed. Permissible stresses for deformed mild steel bars are same as of plain mild steel bars except for bonds. And mild steel bars which have protrusions or deformations on the surface, the bond stress can be increased by 40%, similar to that of deformed bars. Okay. Anyway, once we start seeing some design examples, at that time maybe it will be clear for you. High yield strength deformed bars. These bars are obtained by subjecting mild steel plain bars to cold working by tensioning and twisting. The process increases both yield as well as the ultimate strength of steel. These bars are extensively used in reinforced concrete works and have almost replaced mild steel bars. And typical stress strain curve for these HYSD bars we already looked at, Fe415 500. Okay, this curve differs from that of mild steel due to absence of yield plateau. Since the steel does not possess definite yield point, 0.2% proof stress is used as yield stress. The bars, these bars, that is HYSD bars, have the following advantages. Due to high yield strength, the amount of steel required is considerably reduced. The twisted or deformed bars provide better bond with concrete than mild steel. And end hooks in bars can be omitted. Anyway, we'll see where these end hooks and other things will be coming at a later stage. Okay, usually you require to provide some anchorage and other things. So there we'll be providing these end hooks, and those end hooks can be avoided in some cases. Okay, because of the the better bond between the concrete and the deformed bars. There are some disadvantages associated with the high yield strength steel, namely reduced ductility, lower percentage of longitudinal steel in the beam reduces the capacity of the section in shear. What is this? What is this reduction in the longitudinal relation between the reduction in longitudinal steel in beam and reduction in the shear capacity? We'll see when we solve an example or when we go and look at the design for shear. Okay, so let's complete reading this. The lower percentage of longitudinal steel in beam reduces the capacity of section in shear with a high stress level. The deflection and cracking of the members are large. Anyway, we'll see once we solve some problem, you will understand better. High yield strength bars are available under trade names Tor Steel, and all these are some companies. Okay, Strong and Tiscon, and these bars are available in two grades, Fe415 500, and even nowadays you have Fe550 as well. Okay, recently IS 1786 has introduced a higher grade Fe550. In the grade designation, Fe denotes ferrous material and the number, the yield strength of steel in MPa. These steels lack a definite yield point. Anyway, we already discussed about all this. Okay, so this completes about the steel, and also we noted stress strain curve for steel, design stress strain curve for steel, design stress strain for concrete, and now we are ready for the design. Okay, so any questions here? Any questions? And some details related to fabrication of this reinforcement and placement, and this all what I suggest is I will share with you these slides. You can go through them. These are all self-explanatory, and immediately we may not be requiring all this, so I'm going to skip all this. And formwork is for supporting, or let's go through this formwork once, and then you will quickly complete this. This formwork or shuttering may be defined as the molds of timber, plywood, or steel, or some other material into which freshly mixed concrete is poured at the site, which holds the concrete till it sets or till it hardens. Okay, the formwork includes the total system of support of freshly placed concrete. The formwork should be designed, built accurately, substantially, and efficiently. For designing formwork also, you are required to do analysis, structural analysis, and accordingly design formwork for the loads that are coming on the formwork. Okay, so that is what is mentioned. The formwork should be designed, built accurately, substantially, and efficiently. Okay, and so this purpose of this formwork is mainly to provide some support when the concrete is fresh before it gains strength or hardens. And there are some guidelines. What should be the time when we can remove this formwork? That time is called stripping time. That is what is given, mentioned here, and you can go through all this. Okay, it's all self-explanatory, and this table shows you for different types of structural elements what can be the stripping time. Stripping time in the sense when the formwork can be removed. Because please note that this is very important, this stripping time, because when you have the formwork there, it's difficult for workers to work. So and also to do other things like finishing and other things. So this is very, very important. So this construction industry is very much interested in what is the stripping time. Okay. And for various elements, stripping time is the rough guideline for that is given. And when time required, we can go through it, or if somebody is interested, they can go through this one. Okay, additional information. And Professor Amlan, in his lecture, he showed you various elements in a concrete structural system. And I don't want to repeat all this: slabs, beams, columns, foundations. And he also mentioned about spandrel beam and other things. Okay, main beam, secondary beam. So let's get into the some important aspect. Before we get into the design, we need to make a note of different design approaches. So this table or this schematic gives you a summary of that. Okay, summary of that various design approaches. So please pay attention here. And we are getting into the design stuff. Okay, so initially between 1900 to 1930, initial design approach is working stress or permissible stress method. Working stress or permissible stress method. Okay, and we'll see what are the details about this method, or some of the points related to that method, which are given here. And then later, from 1930 to 1960, another method, another design approach is adopted, that is ultimate load strength method. And most recently, or in the current time, we are using what is known as this limit state method. From 1960 to date, this limit state method is being adopted. So now let's see what is this working stress method. In working stress method, how the design is going to be carried out. Factor of safety is applied on yield or ultimate stress to get permissible stress. You know the grade of concrete you are going to adopt. You know the type of steel that you are adopting. So you know the ultimate strength or yield strength of that particular steel, as well as what is the strength of concrete that you are going to adopt. In this working stress method, factor of safety is applied both on are applied on the yield or ultimate stress to get permissible values. Okay. So some factor of safety is chosen. Let's say I want to have a margin from the yield or ultimate stress value that particular grade of concrete can take, whatever maximum stress that particular grade of concrete can take. I will not allow my stress in the concrete to exceed certain like by a certain factor of that value. So that factor is decided. That factor is like a margin. Factor of safety is applied to the yield or ultimate stress to get the permissible stress value. Structure designed to support working or service loads without exceeding the permissible stress in concrete and steel. So the design is carried out such a way, the structure that is designed is able to support the working load or service load. Working load or service load in the sense when the structure is being used, what are the loads that are going to come on the structure? Taking account all those loads, what are the stresses that are going to be generated? I want to make sure those stresses in the structure are within the permissible value that is calculated based on the first point. Applying the factor of safety, applying the factor of safety on the actual values of yield or ultimate stress of concrete and steel, you are going to get permissible value. I'm going to design the structure such a way the stress that is going to be generated in the structural member is not exceeding those permissible values in steel and concrete. And so this is the design philosophy of this working stress method. Okay. And what is the disadvantage or what are the inadequacies in this method? Inadequacy of this method or inadequacy of this working stress method. Actual safety against ultimate loads is not known. Please note that you are applying factor of safety only on the strength or yield and ultimate strength of the materials you are taking. So actual safety against ultimate loads is not known. Okay. And then an improvement over this is this ultimate load or strength method. Okay. Load factors are applied on working loads, because here you can see here whatever inadequacy that is pointed out in working stress method, that is slightly addressed here. Load factors are applied on the working loads to estimate the ultimate loads. Basically what you are doing is whatever load that is coming expected on the structure, you are applying some load factor on it. So you are going to magnify that value of the load. For design purpose, you are going to multiply with some value like 1.5 or 2. And safety factors are applied on the ultimate strength of the materials. The strength of the permissible stresses in the materials or permissible values that on the strength of the materials are obtained using these safety factors. So load factors are applied on the working loads and safety factors are applied on the ultimate strength of the material. Structure is designed to support the design. Structure is designed to support design ultimate loads. And inadequacy of this method. What is the inadequacy of this method? Serviceability aspects such as deflection and cracking at service loads are not considered. Okay. So from working stress method to this intermediate method, that is ultimate load or strength method, what is the improvement? You applied load factors on the working loads, but still deflection and cracking at service loads are not considered. So an improvement over this is the limit state method. In limit state method, structure is designed to satisfy all limit states, such as limit state of strength, a limit state corresponding to strength. Strength limit state is nothing but you are making sure the collapse is not going to happen. Okay. Limit state of strength and limit state of serviceability. So whatever here inadequacy of this ultimate load or strength method, serviceability aspects such as deflection and cracking are not considered. That is considered in the limit state method. And also, instead of blindly taking some load factors and safety factors without any basis, here statistical probability concepts are incorporated for loads and strengths. Okay. So the partial safety factors that we are going to use in limit states are based on probability concepts, and also characteristic loads and characteristic strengths obtained by applying partial safety factors for load and material strengths. And this method overcomes the inadequacies of working stress as well as ultimate load methods. So the limit state method are actually the design approaches as the time progressed. They addressed whatever inadequacies in the previous approach, that inadequacies addressed in the subsequent approach. And the current approach includes deciding on the partial safety factors from statistical or probability concepts, and also taking care of the limit state of strength as well as limit state of serviceability. Okay, so these are the design approaches. As a part of this course, we'll be touching upon this working stress method. We are going to start with this working stress method, and then once you grasp the concepts, we'll go to the limit state method. Okay, so I think time is running out, and before I close it, here some details are there. You can go through it. I will share with you these slides. So in the next class, we are going to start with this flexural flexural analysis of homogeneous sections or homogeneous materials. Okay, before we go into the concrete, reinforced concrete involves two materials. Okay, before we go to the analysis of reinforced concrete sections, which are composite sections, we'll first look at these homogeneous sections, or sections made of homogeneous materials, for which I require you to go through your mechanics of materials concepts and then come for the next class. Okay, so I'll stop here. Professor Amlan, you want to add something?
Yeah, just as a quick point, see, there is a new type of bars which is called thermomechanically treated bars, TMT bars. Now, these bars are produced by some special treatment process, and their ductility is increased because of this process. We'll be seeing lots of advertisement of these TMT bars. Celebrities promote these TMT bars. Sometimes in a recent ad, I saw the word flexi strong bars. What they mean by flex is actually ductile. These are not additionally more flexible than the other bars, but these are more ductile, and yes, the strength is also retained. Hence, I want to keep you informed that when you see the ads, you note that these bars are now quite prevalent, TMT bars. Okay.
Okay, any other questions or comments? We have few minutes left. No questions?
Are we going to meet tomorrow?
Actually, I'm going to have some commitment tomorrow, but I'm going to send you some information by 3 o'clock tomorrow, 3 o'clock afternoon tomorrow. Anyway, class, our scheduled class is at 5 o'clock. So if you do either way, whether class is there or not, I'm going to send a WhatsApp message to you. Okay. So you will get a link if class is there. You use that link. I'm going to send the link by WhatsApp as well as by email. Okay. As of now, I cannot say tomorrow class is cancelled. Let's hope tomorrow class is going to be there. Okay. And I want you to refresh your mechanics of material background for tomorrow's class lecture. Any other things? It's surprising none of you are asking any questions. Okay, thank you.